Our planet is a place of immense beauty and astonishing power. We often marvel at the delicate balance of life, from the smallest insect to the largest whale. Yet, beneath our feet, a force of unimaginable scale lies waiting. It is a power that has shaped our world for billions of years, creating mountains and oceans. Sometimes this power breaks through the surface in a truly cataclysmic event. We are not speaking of ordinary volcanoes, as destructive as they can be. We are speaking of something far greater, a phenomenon known as a supervolcano. These are not cone-shaped mountains like we often imagine. They are vast, hidden chambers of magma that can unleash devastation on a planetary scale. A supervolcano is defined by the sheer volume of material it can eject. More than 1,000 cubic kilometers of rock, ash, and gas. An eruption of this magnitude is thankfully rare, occurring perhaps only once every 100,000 years. But when it does happen, the consequences are global. The sky can be filled with so much ash that it blots out the sun for years, triggering a volcanic winter. Temperatures would plummet, crops would fail, and ecosystems across the globe would be pushed to the point of collapse. One such event, which took place in the deep past, may have brought our own species closer to extinction than we ever knew. This is not a tale from science fiction. It is a story written in the very rock of our planet, in the layers of ancient ash found thousands of miles from its source, and even within our own DNA. The story of a super eruption is a reminder of nature's ultimate power and of life's incredible fragility. By studying these past events, we can begin to understand the immense challenges our ancestors faced and the remarkable story of their survival. It is a journey back in time, to a moment when a single geological event threatened to change the course of human history forever, leaving an indelible mark on our world and our species. The Earth's crust is a dynamic and restless surface, constantly shifting and changing. Deep below, molten rock churns with incredible heat and pressure. In certain places, this magma accumulates in enormous underground reservoirs, sometimes stretching for dozens of miles. These magma chambers can lie dormant for millennia, their presence barely hinted at by hot springs or geysers on the surface. But if the pressure builds to a critical point, the ground above can rupture, leading to an eruption of almost incomprehensible violence. This is the mechanism of a supervolcano, and understanding it is key to appreciating the story of our planet's most dramatic chapters and our own precarious existence upon it. Our story takes us back approximately 74,000 years to the Pleistocene epoch. At this time, early modern humans, Homo sapiens, were beginning to explore the world, living as small bands of hunter-gatherers. They were skilled and adaptable, but they were about to face a challenge unlike any other. On the island of Sumatra, in modern-day Indonesia, a geological time bomb was ticking. Beneath the lush tropical landscape, a vast chamber of magma had been growing for hundreds of thousands of years. When it finally erupted, it became what we now call the Toba super eruption, quite possibly the largest volcanic event on Earth in the last 2 million years. The scale of the Toba eruption is difficult to comprehend. It was thousands of times more powerful than any volcanic eruption in recorded history. Scientists classify eruptions on the Volcanic Explosivity Index, or VEI, a scale from 0 to 8. The 1980 eruption of Mount St. Helens was a VEI 5. The colossal 1815 eruption of Tambora was a VEI 7. Toba was a VEI 8, the highest possible rating. It unleashed a torrent of energy equivalent to thousands of nuclear bombs, fundamentally altering the landscape not just of the island, but of the entire planet. The sound would have been deafening, heard for thousands of miles. The eruption was not a single, simple blast. It was a sustained, cataclysmic event that likely lasted for weeks. It tore a hole in the Earth's crust so large that the ground above the emptied magma chamber collapsed. This collapse formed a massive depression in the ground known as a caldera. The caldera left by the Toba eruption is truly immense, measuring roughly 100 kilometers long and 30 kilometers wide. Over thousands of years, this enormous scar on the Earth's surface filled with rainwater, creating the tranquil and beautiful Lake Toba we see today, a serene mask hiding the memory of unimaginable violence. The location of the Toba eruption in Indonesia placed it at a crucial crossroads of the ancient world. The ash and gases it spewed into the atmosphere were carried by global wind patterns, spreading a blanket of volcanic debris across Southeast Asia, the Indian subcontinent, and beyond. For the small populations of early humans and other animals living in this part of the world, the immediate effects would have been apocalyptic. Vast areas would have been buried, ecosystems destroyed, and the very air made toxic. This single event, happening in a corner of Southeast Asia, was about to have profound consequences for every living thing on the planet. To truly grasp the power of Toba, we must look closely at what happens during a super eruption. It is not simply a fountain of lava. When the pressure from the magma chamber below becomes too great, the crust above fractures and shatters. This allows superheated gas, magma, and rock to explode outwards with phenomenal force. One of the most terrifying products of such an eruption is the pyroclastic flow. This is a fast-moving, ground-hugging avalanche of hot gas, ash, and volcanic rock fragments, known as pumice, that can travel at hundreds of kilometers per hour. These flows are incredibly destructive, incinerating everything in their path with temperatures of many hundreds of degrees Celsius. The Toba eruption produced an astonishing volume of this material. Geologists estimate that it ejected at least 2,800 cubic kilometers of dense rock and ash. To put that into perspective, this is enough material to cover the entire United States in a layer of rock and ash deep enough to bury a one-story house. The immediate area around the volcano would have been completely sterilized, buried under hundreds of meters of hot volcanic deposits. This is not soil or dust. It is a thick, heavy blanket of shattered rock and glass that would have transformed a tropical paradise into a desolate, gray wasteland in a matter of hours. The finest material ejected from the volcano is volcanic ash. These are tiny, sharp fragments of rock and glass, pulverized by the force of the explosion. Unlike the ash from a wood fire, volcanic ash is abrasive, heavy, and does not dissolve in water. When inhaled, it can be lethal to living creatures, clogging their lungs. When it falls in thick layers, its sheer weight can cause buildings to collapse. The Toba eruption sent a colossal plume of this ash high into the atmosphere, more than 40 kilometers up into the stratosphere. From there, it would be carried by high-altitude winds, destined to travel across the entire globe. This ash is the key piece of evidence that allows scientists to trace the eruption's global impact. Geologists have found a distinct layer of Toba ash, known as the youngest Toba tuff, in sediment cores drilled from the ocean floor and in archaeological sites across Asia and as far away as East Africa. This layer provides a precise marker in the geological record, a single moment in time preserved for 74,000 years. It allows us to directly connect events happening in different parts of the world to the Toba eruption, giving us a powerful tool to understand its far-reaching consequences for the planet's climate and for life itself. The most profound and long-lasting effect of the Toba super eruption was not the immediate devastation, but its impact on the global climate. The immense column of ash and gas that rocketed into the stratosphere contained millions of tons of sulfur dioxide. Once in the upper atmosphere, this gas reacts with water to form tiny droplets of sulfuric acid, known as sulfate aerosols. These aerosols are highly effective at reflecting sunlight back into space. With a vast cloud of these particles encircling the globe, less sunlight could reach the Earth's surface. Planet Earth was suddenly and dramatically shaded from the sun. The result was a phenomenon known as a volcanic winter. Global average temperatures would have plummeted. Some scientific models from the past, such as a study from 2009, have suggested a catastrophic drop of as much as 14 degrees Fahrenheit, pushing the planet into a sudden and severe cold spell that could have lasted for several years, possibly even a decade. The skies would have been perpetually dim and gray, a world of constant twilight. Photosynthesis, the very foundation of most life on Earth, would have been severely hampered. Plants would have struggled to grow, leading to widespread ecosystem collapse on land and in the oceans. The evidence for this climatic shift is written in the geological record. The ash from Toba is found in ice cores from Greenland and Antarctica. An analysis of the ice layers from that period shows a sharp spike in sulfate concentrations, followed by a period of significant cooling. The ash itself traveled astonishing distances. Scientists have found layers of Toba ash blanketing the entire Indian subcontinent, in some places several meters thick. It has been discovered in the South China Sea and across the Indian Ocean, providing a stark testament to the eruption's sheer scale and the efficiency of atmospheric circulation in spreading its impact worldwide. For the small populations of early humans living at the time, This would have been a terrifying and bewildering experience. The world they knew would have changed overnight. The sun, the source of warmth and life, would have grown weak. The seasons would have been thrown into chaos, and the animals and plants they relied on for survival would have become scarce. It was a global environmental crisis of a magnitude that modern humans have never experienced. The question that has fascinated scientists for decades is, how did our ancestors survive? And what did it take to endure a world plunged into darkness? The timing of the Toba eruption, around 74,000 years ago, coincides with a fascinating period in our own evolutionary history. For years, some geneticists have pointed to evidence within our DNA that suggests humanity experienced a population bottleneck around this time. A bottleneck occurs when a species' population is drastically reduced to a very small number of individuals. According to this theory, the global environmental crisis triggered by the Toba supereruption may have been the cause. The sudden, prolonged cold, the failure of food sources, and the general devastation could have pushed our species to the very edge of extinction. This Toba catastrophe theory suggests that the entire human population may have dwindled to just a few thousand individuals, perhaps even as few as 1,000 breeding pairs. If this were true, it would mean that every person alive today is a descendant of this small, resilient group of survivors who somehow managed to navigate a world that had become intensely hostile. The genetic diversity seen in modern humans is relatively low compared to other great apes, which could be explained by our ancestors passing through such a narrow population bottleneck. This idea paints a dramatic picture of a near-extinction event, a close call that almost ended the human story before it had truly begun. The main evidence for this bottleneck comes from studies of mitochondrial DNA, which is passed down from mother to child. By analyzing the genetic variations in people from around the world, scientists can create a kind of family tree and estimate population sizes in the distant past. Some of these studies point to a sharp reduction in population size somewhere between 50,000 and 100,000 years ago, fitting neatly with the timing of the Toba eruption. This genetic evidence, combined with the clear geological evidence of a massive global event, created a compelling and powerful narrative about our species' fight for survival. However, this theory has become a subject of intense scientific debate. While the genetic data is intriguing, it is not definitive proof. Interpreting population history from genes is a complex science, and different methods can yield different results. Furthermore, as archaeologists have scoured the globe for clues, they have begun to uncover a different story. They have found evidence that in some parts of the world, human populations did not just survive the aftermath of Toba. They may have actually thrived. This has led to a fascinating scientific puzzle, pitting the dramatic story in our genes against the tangible evidence left in the ground. To find evidence of human survival, we must travel far from the eruption itself, all the way to the southern coast of Africa. Here, at a series of archaeological sites known as Pinnacle Point in South Africa, scientists have made a remarkable discovery. Buried in the layers of ancient sediment within coastal caves, they found a thin but distinct layer of microscopic glass shards. When they analyzed the chemical composition of these shards, they found a perfect match for the volcanic ash from the Toba eruption over 9,000 kilometers away. This was the smoking gun, a direct link between this site and the global catastrophe. What makes this discovery so extraordinary is what was found directly above and below this ash layer. The caves at Pinnacle Point contain a rich record of human occupation spanning thousands of years. Far from showing evidence of a population collapse, the archaeological record revealed continuous and even intensified human activity. A discovery from 2011 unearthed over 400,000 stone artifacts, along with clear signs of fire use, packed into the layers around the time of the Toba event. It seems the people living here were not struggling to survive. They were busy, innovative, and thriving in their coastal environment. The key to their success appears to have been the unique resources offered by the coast. While inland ecosystems may have been devastated by the cooling climate, the oceans are more resilient to sudden temperature changes. The people of Pinnacle Point were experts at exploiting the rich marine food web. They gathered shellfish from the intertidal zone, a reliable and nutrient-rich food source that would have been less affected by the volcanic winter. This coastal adaptation may have provided a crucial buffer, a refuge, that allowed them to weather the worst of the climatic disruption caused by Toba, while inland groups may have struggled. This evidence paints a picture not of near extinction, but of human ingenuity and adaptability. These early humans were not passive victims of a natural disaster. They possessed complex cognitive abilities, including the knowledge of how to find and process different types of food, how to control fire, and how to create sophisticated stone tools, some of which were heat-treated to improve their quality. The discoveries at Pinnacle Point and other sites in Africa suggest that while Toba was undoubtedly a massive global event, its impact on humanity may have been more complex and varied than a simple story of near annihilation would suggest. The compelling evidence of human resilience from places like Pinnacle Point has led scientists to re-examine the Toba catastrophe theory. While no one doubts the immense size of the eruption, the debate now centers on the severity and duration of the volcanic winter it caused. The original models that predicted a catastrophic global temperature drop of up to 14 degrees Fahrenheit have been challenged by newer, more sophisticated climate simulations. These recent studies suggest that the cooling effect may have been significant, but perhaps not as extreme or as long-lasting as once thought. One key factor in this new thinking is the behavior of the sulfur aerosols in the stratosphere. The earlier models assumed that the sulfur would spread out evenly, creating a uniform blanket that would block sunlight for a decade or more. However, some newer research suggests that with such a massive injection of sulfur, the aerosol particles may have clumped together into larger particles. These larger clumps would have fallen out of the atmosphere much more quickly, perhaps limiting the most severe global cooling to a period of about 3 years, rather than 10. This would still be a dramatic climate shock, but perhaps one that was more survivable. This has led to a revised view, where the most devastating impacts of Toba may have been regional rather than truly global. The Indian subcontinent, for example, was directly in the path of the ash fall and would have experienced complete environmental collapse. For any human populations living there, the eruption would have been an unsurvivable event. However, for groups living much farther away, such as in Africa or Europe, the effects might have been less severe, perhaps a few years of cold, difficult winters and disrupted food supplies, but not an existential threat that pushed them to the brink of extinction. The scientific consensus is still evolving, and the debate is far from over. The amount of sulfur released by Toba remains a point of contention, and different estimates lead to very different climate outcomes. What is clear is that the story of Toba and our ancestors is more nuanced than we first believed. It is a powerful lesson in how science works, with new evidence and new technologies constantly challenging and refining our understanding of the past. Toba may not have been the single event that nearly wiped us out, but it was undoubtedly a formidable test of our species' ability to adapt and endure. The Toba eruption serves as a stark reminder of the power that lies dormant beneath the Earth's surface. While a super eruption on that scale is exceedingly rare, our planet is home to many other powerful volcanoes that pose a significant threat today. As of early 2026, scientists are monitoring around 45 volcanoes that are showing signs of unrest worldwide. Many of these are located in densely populated areas, making the risk to human life and infrastructure immense. The lessons learned from past eruptions, both large and small, are crucial for preparing for the future. In the United States, volcanoes like Mount Rainier in Washington are considered particularly dangerous. Rainier's great height means it is covered in massive glaciers and snow fields. An eruption could melt this ice, triggering enormous volcanic mudflows, known as lahars, that could surge down river valleys and inundate communities like Tacoma. Yellowstone in Wyoming is, of course, a supervolcano itself, though its last major eruption was 640,000 years ago, long before humans existed. While recent hydrothermal activity, there is not a sign of an impending eruption, it reminds us that the system is very much active. Globally, the threat is just as real. In Japan, Mount Fuji has not erupted since 1707, but pressure may have been building beneath it since the massive 2011 earthquake, and an eruption today could affect the 25 million people living in the greater Tokyo area. In Indonesia, the nation with the most active volcanoes, Mount Merapi erupted as recently as January 2024. Over 24 million people live in its vicinity. The 1991 eruption of Mount Pinatubo in the Philippines was the second largest of the 20th century, and its cooling effect on the global climate was carefully studied, providing vital data for our models of volcanic winters. These modern volcanoes, while smaller than Toba, highlight a different kind of risk vulnerability. In the 74,000 years since Toba, The human population has grown exponentially, and we have built vast cities and complex global networks for trade and travel. An eruption the size of Pinatubo today would cause far more economic disruption than it did in 1991. A much larger eruption, even one far smaller than Toba, could trigger a global food crisis, ground all air travel for months, and cause widespread social and political instability. The giants are still with us, and we are now living right at their feet. In the face of such immense natural power, it would be easy to feel helpless. But humanity is no longer living in the Stone Age. Today, we have science on our side. Around the world, dedicated teams of scientists at volcano observatories, like the Yellowstone Volcano Observatory in the United States, work tirelessly to monitor these sleeping giants. Their mission is to listen for the subtle whispers that might signal a volcano is waking up. This is a complex and vital task that combines cutting-edge technology with decades of geological expertise to keep people safe. Volcanologists use a wide array of tools to keep a constant watch. Networks of seismometers detect the tiny earthquakes caused by magma moving deep underground. GPS stations and satellite radar can measure subtle changes in the ground surface, detecting swelling or tilting as a magma chamber inflates. Scientists also monitor the gases being released from volcanic vents, as changes in the composition, such as an increase in sulfur dioxide, can be a key indicator of an impending eruption. Webcams provide visual monitoring, like the one that captured a small eruption at Yellowstone's Black Diamond Pool in May 2025. This constant monitoring allows scientists to provide warnings to governments and the public, often weeks or months in advance of an eruption. The successful evacuation of tens of thousands of people before the 1991 eruption of Mount Pinatubo is a prime example of modern volcanology in action, a success that saved countless lives. By understanding a volcano's history and monitoring its present behavior, scientists can create hazard maps that show which areas are most at risk from lava flows, pyroclastic flows, or lahars, allowing for better land use planning and emergency preparedness. The story of Toba is therefore not just a tale of ancient catastrophe. It is a vital lesson for our modern world. It teaches us about the planet's capacity for dramatic change and the importance of resilience. By studying the ash layers, the ice cores, and the archaeological records, we learn how the Earth system responds to such shocks. This knowledge helps us refine our climate models and better predict the consequences of a future large eruption. In listening to the echoes of the past, we learn how to better protect our future. We can never tame the power of a volcano, but by listening closely, we can learn to live alongside it.